Let's consider the function f of x and y equals x squared y cubed plus 1 at the point 2, 1. And we'll do a few things with this. Let's first consider the question of finding the tangent plane, the plane which is tangent to the graph of that function at this xy pair, 2, 1. Now, a general formula for the tangent plane, the way I like to write it is a sort of natural extension of the point slope formula, where we have z minus z naught is equal to the slope in the x direction, which I'll call m sub x, times x minus x naught, plus the slope in the y direction, which I'll call m sub y, times y minus y naught. Again, if you consider holding either x or y to be constant and equal to x naught or y naught respectively, you'll see that this simplifies down to the ordinary point slope equation of a line in the appropriate direction. So let's work on finding what we need here. Well, to find slopes, of course, we're going to need the partial derivatives. So let's compute those. F sub x at a generic xy point. We'll take the partial derivative of this with respect to x. That looks like 2xy cubed. And f sub y, taking the partial derivative now with respect to y, that looks like we get a 3x squared y squared. The 1 being constant goes to 0 in both cases. Now, we specifically want the slopes at this point, 2, 1. So the slope in the x direction, m sub x, is f sub x at the point 2, 1. And plugging in those for x and y, that looks like 4. And the slope in the y direction would be f sub y at 2, 1. And substituting that, it looks like we have 4 times 3 is 12. Whenever finding tangent planes or linear approximations, do make sure to evaluate your partial derivatives at the point of interest. Some students find these partials and then just stick them in here, and then you get these ugly nonlinear equations that can't possibly be planes because they aren't linear, right? If you have a 2xy cubed in the middle of this thing, that is not going to give you a tangent plane. Remember that these partial derivatives describe the tangent slopes at all of the points in the domain of f. And we're looking for a particular tangent plane just at this point right here. There are infinitely many tangent planes. We need to figure out which one. So we have to compute those slopes there. Okay. So that gives us those slopes. The only thing we're missing here is this value z naught. Now, if z is equal to f of x and y, then z naught is the value of the function at the point in question. So let's see if I can squeeze that in here. Z naught is equal to f of 2, 1, which equals, that's 4 plus 1 is 5. So now plugging in everything we have, z minus z naught is 5, equals the slope in the x direction times x minus x naught plus the slope in the y direction times y minus y naught. So we have the equation z minus 5 equals 4 times x minus 2 plus 12 times y minus 1. That is linear with x, y, and z, so that describes a plane, and this is one way of writing an equation of the tangent plane to the graph of that function at the point in question. Now, depending on what you want to do with this equation, you might leave it like that, or you might rearrange it and simplify it a bit. I believe I mentioned back in chapter 12 the same sort of issue. Sometimes we want to clean this up a little bit. and sometimes not. It depends on what we're doing. If we do want to simplify it a little, we could add 5 and distribute those things. So we could write z equals 4x minus 8 plus 12y minus 12 plus 5 from that other side there. And that would give us z equals 4x plus 12y minus 8 minus 12 is a negative 20 plus 5 leaves negative 15. So this is a much simpler expression for the tangent plane. And for some purposes, this would be much preferred. In particular, if you're going to be, typing something into WebAssign, it might accept the first one. I haven't really tried, but it should accept this last one, this fully simplified version. And the less you have to type, generally, the less chance there is for error and things like that. On the other hand, you want to be careful because every time you do algebra, distributing and solving and combining terms, there is a chance for error. So you want to figure out for yourself what the best way to enter these things would be. So that's how we find tangent planes. Like I said, it's basically just an extension of how we do, how we use the point slope form of a line to find a tangent line to a curve, like back in Calc 1. Now, if we want a linear approximation of f at the point 2, 1, well, you could use the linearization formula that's given in the textbook, or you could remember that just like a tangent line is a linear approximation to a curve in a single variable setting, the tangent plane is a linear approximation to a surface. So the linearization L of x and y will simplify down to whatever we got as our tangent plane, just in place of z, right? Depending on what you're doing, you might not even need to write out this L of x and y. Just the tangent plane z equals 4x plus 12y minus 15 is the best linear approximation to the function at the point in question. Now let's look at using this. Suppose instead of f of 2, 1, which was fairly easy to mentally compute, maybe we want to approximate the value of f at another point. Let's find the linear approximation of f at 2.01, 0.98. And now if you think about trying to do this mentally, it's maybe not too hard to square 2.01, but when it comes to cubing 0.98, that is a bit cumbersome to do by hand. Now, hopefully you're reading my notes that I posted. I talk about at the end of those why we actually care about linear approximations. It's not about mental estimates. There are much more important reasons for this. But the notion of thinking about how easy is something to compute by hand is kind of a proxy in these very simple examples. It's kind of a proxy for the more complicated computational instances you might run into in practice. Even when you're using a computer, sometimes it can be advantageous to cut down the time required to evaluate a function. So with these little toy examples like this, we can imagine that we don't have a calculator and we're trying to do this by hand. And that gives us a sense of the relative computational difficulty of different operations. Cubing is more difficult than just a single multiplication, for instance. So evaluating the original function might be a little bit tricky, but let's try this linear approximation and see what that does for us. We'll use this value here, so we'll take 4 times x. Now x is 2.01, plus 12 times y, 0.98, minus 15. So we have, that looks like an 8.04, plus, now this will be a little bit trickier, but if we take a 12 minus 0.24, so we'll have an 11.76, if I'm doing that right. minus 15. 8 and 11 is 19. Minus 15 gives us 4 point, and a 0.04 and 0.76 is a 0.8. Let me check my notes, and yes, 4.8 is indeed what we get there. So apparently my mental arithmetic has worked. And we find that the linear approximation to our function at this value right here is 4.8. Now, is that any good? Let's find out. This function actually is not hard to evaluate if you use a calculator or computer. And if we evaluate our function at that point, so we'll take 2.01, 0.98, plugging that into the original function, x squared y cubed plus 1, with a computational device of choice, we find that that is approximately equal to 4.8025, which is fairly good. Now, we were very close to the point in question, right? These are very tiny adjustments. If you drift further away, the approximation will be less good. And this is a fairly well-behaved function that doesn't change too rapidly. But this does illustrate the point that depending on how much accuracy is necessary, a linear approximation may do the job pretty well. Now, there was still some difficulty here when we had to, for instance, multiply 0.98 times 12. If you ever find yourself working on these things by hand, which I don't think will happen this semester, but traditionally in our calc and diffie-q sequence, we often disallow calculators on in-class exams. So you do want to make sure that you can do as much as possible by hand. And for that purpose, let's actually come back to this earlier plane equation that we have. This z minus 5 equals 4 times x minus 2 plus 12 times y minus 1. Let me recopy that down here. Z minus 5 equals 4 times x minus 2 plus 12 times y minus 1. Now again, if we want to approximate this at the point 2.01, 0.98, now we plugged this into the simplified plane equation, but what if we go back into the original plane equation? So we have z minus 5 equals 4 times x is 2.01. We have minus 2. Plus 12 times y is 0.98, minus 1. Let's start simplifying and also solving for z. Well, let's not isolate z just yet. Let's leave this as z minus 5 in this step. Simplifying what's in the parentheses, 2.01 minus 2 is just 0.01. 0.98 minus 1 is, of course, a negative 0.02. So now we have z is equal to, these are much easier to multiply, right? 0.04 minus 0.24 plus 5, the 5 coming from the minus 5 on the left. 0.04 minus 0.24, that's going to be a negative 0.2. 5 minus 0.2 is 4.8. And that was the same approximation that we got above. So a couple of points here. One is that any form of the plane equation will work. Whatever equation you have for your plane, that is a linear approximation. You can plug into any of those and evaluate to find out what z is to get your approximate value. In the case when you're doing things by hand, you might find it very useful to do the subtraction or addition as appropriate, but handling that offset, if you have only a small change from the point in question, which it should always be a small change, right? If you aren't given, here we started off with a question about the 0.21. If you weren't given that point and you were just asked to use a linear approximation to approximate the value of f of 2.01, 0.98, what you should do is kind of round to the nearest integer, 2 and 1, or other numbers that are easy to evaluate for your function. It depends on what kind of function you're dealing with. Maybe, if you have a logarithm or a trigonometric function, then maybe something based on e or pi would be easier. You want to try to find something, a number that's nearby, very close, as close as possible. It's also easy to compute with and deal with that. And if you plug that into the form that has like your x minus x naught, y minus y naught, and you do that subtraction first, you will often end up with numbers that are much easier to deal with. And then when you do those multiplications, you can evaluate that accordingly. That is not only a point for doing things mentally or by hand when you don't have a calculator or a computer, but this can also be useful within the code of a computer or calculator. If you go on to a course like Applied Numerical Methods or otherwise study some issues of round-off error and numerical stability and whatnot, very frequently if we're just using some floating point standard, there are only so many digits of accuracy stored in the computer, stored in memory. So if you have a fairly large number, I should say if you have a lot of digits being multiplied by a number, then the result might not have as much accuracy as you could get if you have, if you do the subtraction first to find out what your differences are, and then multiply those by the appropriate numbers. In some situations, that can get you a bit more accuracy. Sometimes not. It kind of depends on what you're dealing with. Depending on your particular field of study or work, you might want to look into those numerical issues a bit further. But that's the rough idea of linear approximations. Related to this is the notion of differentials. Let's approach the same general function and idea through the lens of differentials. So we have the total differential dz is equal to the partial of z with respect to x times the differential dx plus the partial of z by y times the differential dy. Again, note the difference between the ordinary differential d's for the differentials dz, dx, and dy, and the partial curly d's for the partial derivatives, the partial of z by x and the partial of z by y. These are different from each other. These partial derivatives, even though they look a bit like differentials, do not work like differentials, as you can see. If this was just dz by dx, we would say that the dx's cancel and the dy's cancel, and then you have dz plus dz is 2dz, and that can't equal dz, right? This does not make, that would not make sense. These are just partial derivatives. They don't tell the whole story. So unfortunately, we can't work with the partial derivatives as if they were differentials like we can with ordinary derivatives. But we could do several things with this. One thing we could do is to find a general expression for the total differential dz by evaluating these partials. The partial of z by x, assuming, with the understanding that z is equal to our function value f of x and y. That partial derivative then is 2xy cubed. So we have that dx plus the partial by y gives us a 3x squared y squared dy. So this expression here would tell us what the differential dz is in terms of dx and dy at any xy point we choose. So in particular, at the point 2, 1, for instance, plugging those in, 2 and 1, we get 4 dx plus 12 dy. And for any sort of linear approximation purposes, we will also want to find out what our value z naught is, or just z, depending on which notation you're trying to use here. And let's go ahead and compute that as we did the first time we tackled this problem. That's just going to be the function value at the point in question. Plugging into 1 looks like 5. Okay. So when you're dealing with problems like this, you want to pay attention to the context of what is being described and look at what the point is that you're being given. You might be asked about the point 2, 1, in which case that implies that this is an xy ordered pair. And for finding anything with tangent planes, you will then have to compute to find the z value that corresponds to that with 5. Alternatively, you might sometimes be given a point like 2, 1, 5, and then you can understand that to mean that, oh, this is your xyz ordered triple. And the z value is already given to you. In that case, I would suggest checking to make sure, plug in your x and y to make sure that you get that value for z and that everything is consistent. But at least in theory, the z value would be provided for you in that context. But do note the differences of the ordered pair versus the ordered triple. They mean different things. They're providing different amounts of information. Don't assume a z value to be 0 just because it isn't listed there. I've seen students do that plenty of times where they just let z0 be 0 because there's no z0. That's not how this works. Z is always understood to be the value of the function. So if you have an x0, y0, and you have a function, there is a z0. It may happen to be 0, but most of the time it won't be. If you aren't given z0, you will need to compute that yourself. But anyway, we have that here. So how can we use that? Well, we found our z0, and we have our total differential dz. So that is all the information we need to do any sort of nearby linear approximations. So for example, using that same point I had before, 2.01, 0.98, let's find dz. So dz is 4 times dx. So what's dx? Well, dx is the amount of change in x. This was computed at 2, 1, so our x value was 2. We're looking at 2.01. How much did the x change? The x increased by 0.01, so we have a positive 0.01 there. And now we have plus 12 times dy. Well, what's the change in y? From 1 down to 0.98. That's a change of negative 0.02. So there's our dy. So we have those values. Now we can multiply that out. We have 0.04 minus 0.24, and that is negative 0.2. There is dz. All right. So the idea now is that if we want to approximate the function value f at 2.01, 0.98, this would be, well, z0 gives us the function value at 2, 1, and there is some change, delta z, that would be added to z0 to give us the new function value. And the idea is that if we are sufficiently close to the point where we're approximating these things, delta z is approximately equal to dz. So z0 plus delta z is approximately equal to z0 plus dz. Z0 is 5. Dz we found to be negative 0.2, and 5 plus negative 0.2 is 4.8. And that, you might recall, is the approximation that we found just a few minutes ago, using the method with the tangent planes and or linearization. So these two methods, the tangent plane method and the use of differentials, these two methods are algebraically equivalent. They give us the same results. They're just very different ways of thinking about and organizing the information and handling the bookkeeping. The differentials focuses on relative change and finds out how much of a change there is as we move from the simple point to this other point where we want to compute, and then apply that change to the function value. The tangent plane approach has more of a linear approximation idea. We have this tangent plane, and we're kind of replacing the function with a linear function that is simpler to evaluate, and then evaluating that at the point in question. A couple different ways of going at this. In many problems, you can choose whichever one you want. I recommend trying them both, either trying out both methods on the same problem and making sure your results are consistent, that they match each other, and comparing and contrasting what you do along the way. As you go, you will probably find that you prefer one over the other, and then you can more or less stick with that unless you have a reason to switch. Do make sure that you can do both of them, because if you're asked to find the tangent plane, it's a little hard to get that from the differentials. You can, but it takes more work. It's much easier if you can just do the tangent plane computation directly. On the other hand, there are certain kinds of questions about estimates of error and computing relative error and things along those lines that are much easier to do with differentials, because then you don't have to compute as many other things. You can focus on just what matters, which is computing the changes. There are examples of those things in the textbook. Both methods have their uses, but again, you can see that we get many of the same numbers as we work through. We're doing a lot of the same things, just kind of organizing it differently and thinking about it differently.